In this block, I am going to show you 3 examples. 2 of the examples are linear model, and I am going to show you one non-linear model. What is linear and non-linear? I am going to present these at the end of the problems. So let us consider this very simple cruise model. We have got a vehicle. The mass of the vehicle is m, it is given. There is an accelerating force denoted by F. It is acting on the car. Of course, this F is contacting with the tires and powertrains and so on, but it is not important now from the modeling point of view. What is BV? BV is a resistive force, V is the speed of the car, and B is a constant. So everything is constant in this model, the M and the B. So this is why our model will be linear. We will see it in the equations, of course. So this is the very first and a very simple model of a cruise control problem, because the purpose of control is to maintain a constant speed. Why the speed can change if we have got a constant speed that has been set before? Because of some external disturbances. For example, there is a wind, there is a road grade, and so on. So this is why we need a controller. But now we would like to set up the model of the plant. So everybody knows that the Newton equation looks like as follows. MA is equal to F minus BV. So MA is the force acting on the car. It is F minus BV. So F is decreased by BV because they have got opposite direction. But now I would like to present a model which variable is V, the velocity of the vehicle. So that's why we are going to write the following. mv dot is equal to F minus BV. So in this equation, we have got only V, the velocity, and the V dot, the time derivative of the velocity, which is the acceleration of the car. But this equation contains only one unknown, and this is the V. So this is how to prepare the equation, and from this we are going to write the following. V dot is equal to minus B over mv plus 1 over mf. This equation is called ordinary differential. So this is the coding of this problem. Differential equation because we have got time derivative in the equation, and ordinary because the v is only depending on the time. So it's not a partial differential equation. So this is an ODE, and this kind of model we usually need for controller design. So if I put this to this box, so V dot is equal to minus B over M V plus 1 over M F. The input is F for this problem and the output is V. So this is a very simple application in this case. So this point, the force F, we are going to call it as input, and the V, because it has got V dot in this equation here, we are going to call this variable later state variable. State variable. State variable will be the variable which we have the time derivative inside the equation. So now V is the state variable. So we usually have one input. Now this is the force, and we will have some state variables later, and there will be an output of course, but the output now is the velocity of this cruise. There is a very nice representation of these problems. So if we have got an ordinary differential equation, we can draw a graphical representation of that. It can be important because of the software, because the software input can be a graphical representation. Usually we need an integrator. The integrator has one input and one output. The input in this case is usually the v dot, and the output is v. From the equation, we can see that v dot is equal to the sum of the two parts. I repeat the equation here. V dot is minus bm v plus 1 over m f. So there is usually a part which is depending on the state variable itself. So now it is depending on the velocity. So I just feed this back to the input, and we have got a gain which is minus b over m. So this graphical representation is v dot is equal to minus b over m f. And now I have to add an extra term which is 1 over m f. So I put a box here which is a gain of 1 over m, and the input here is the force F. And now this is the graphical representation of this equation, and this will be the output of this system. So in the software that we can use for control and design and for system analysis is the first one, which I represented here, this one. So just draw a box and just write the equation inside this box. And the second one is this one, which is the graphical representation of the whole system equation.